This is a photo of New York City, and from what you can see is this phenomenon of the last few hundred years of large infrastructures, large villages like New York, built up essentially around the beach, where we like to live and to play. And from New York, where my home university, looking at that environment back to the bigger picture of the globe and stopping and catching that there are these large features, ice sheets, Greenland and Antarctica further down to the south, and thinking forward about what we know and what we don't know about the future of those ice sheets and what it means to sea level. And so we can take a look in this particular place we are tonight, Abu Dhabi, and like New York in some sense. My university has an interest in New York City and here, and so we're going to look at the relation between these two cities in terms of future sea level. This is Abu Dhabi, and again you can see yesterday we walked along this very nice path, the Corniche, and again the idea that the ocean is close by. In fact, we shot some video of this yesterday and had some spare time in the afternoon, and it was nice and people were out having fun, like this guy here. So the setting for this problem is to think of really what we've been really focusing on, I guess, for the last 6 decades, when people really became aware of environmental science, the science of understanding the Earth as a physical and a biological system. The first time I really became interested in environmental science is I remember watching the NASA moon landings and the video that came out of that. I have a little clip here from that.
11, Houston, if that's not the Earth, we're in trouble. That's the Earth, and we have a very good view of it today. There are a few more cloud bands on than yesterday when we beamed down to you, but it's a beautiful sight.
So really the problem in environmental science is to think about the evolution of that planet, the ocean, the atmosphere, the land systems, and one component that has received less attention maybe than it should are the 2 large ice sheets. So moving away from the general question of environmental science to a more specific one, and one could think of many questions in environmental science, but the one we're going to focus on for the next little while is that of sea level, a very specific question. And I want to give you a sense of the things that we do and do not know about that aspect, because I guess to people who don't study this closely, there's a real distinction I want to bring out about things where we have credibility and where we have technical skill, and places that we're not yet there. So quantifying the risk is the name of the game. We want to associate numbers with the question of sea level rise. What do we know? This is a very important data set. As far as I can tell, this is the foundation of climate change science. This is a 100-year data record. It shows temperature on the planet. Red is temperature above 2 degrees. And the picture that's shown here says that the planet has warmed by this amount, which I think globally averaged is about 1 degree Fahrenheit or just over ½ degree centigrade. So that's a data set. And the implication of this, whereas this is data and very robust, the implication is just shown by this picture that a warmer planet will melt its ice sheets and that sea level will change. So we can put good numbers on the temperature part, but putting good numbers on this part turns out to be a very difficult thing to do. Why does it matter? That may be obvious. Lots of our major cities, a few listed here, would be affected greatly, if not flooded, by large sea level change. None the least, also New York and Abu Dhabi, the 2 that I'm thinking about presently. There is no shortage of media coverage on this topic. When one thinks of the broader topic of climate change, people ultimately ask, what does that mean? And sea level is certainly among the top 1 or 2 or 3 things that people think about as tangible impacts. And so you'll see much in the media with sketches of cities, and it's kind of like parts of it are flooding and whatnot. And the same with Abu Dhabi, 2100 underwater, etc. And what it is people have an idea that there's a potential impact, but making it a bit more substantive is what we really want to do. So what would be an obstacle? Why is it that we can do a certain part of the science and we have trouble with another part? It's kind of wrapped up in technical details like this. This is an image shot from the Greenland ice sheet. So the Greenland ice sheet is this piece of land in the background with a large piece of ice sitting on it. And the ice cracks off or calves and flows into the ocean. The moment that ice goes from high on land down into the ocean, which is what you saw happen in this video, the moment that happens, and that's about twice the height of the Empire State Building, that's a big piece of ice, that process, which is totally natural, raises sea level. And when water evaporates from the ocean and falls onto the ice sheet in the background, that lowers sea level. And that's the ice sheet story in a sense. And the physical description and the mathematical description of that process essentially does not exist, part one. And getting to these places turns out to be very difficult. Getting to Greenland is somewhat difficult. Getting to Antarctica is not as difficult as getting to the moon, but it's somewhere in between. It's a challenge. So how does sea level change? There's two ways you can change sea level. You can heat the global ocean, and for the last 5 decades, the global ocean has been warmed by 0.5 degree centigrade because we have floats in the ocean that measure it. And when you heat water, it expands. That part is relatively well understood. Also, you can change sea level by adding water. That is the last video when you saw large icebergs calving and going into the ocean. That process raises the global sea level. So we are definitely adding heat to the atmosphere and the ocean. That's a data record. How much water are we adding from land ice? That's also a data record. And right now it's about 1/3 of the observed global sea level coming from heat, 1/3 from water, and 1/3 still a little uncertain. And really the question is, going forward, this red arrow will represent some modest change in sea level, but the part about the ice sheets, the question mark, may represent a very large change in sea level. Certainly in the past it has. For example, going back just 15,000 or 10,000 years, sea level was 100 meters or 120 meters lower than today. So naturally, sea level changes a lot. The media for the last decade, perhaps, and policy are far ahead of scientists on this issue, in the sense that we have not done an adequate amount of research on our own planet of this phenomena to really be able to simply make projections going forward. So there are many stories out there that capture people's attention, and they may be right or they may be overstating the problem. In either case, what I would assume would want to do in the coming decade or decades is to really put together large efforts to sort this question out, and I suspect we could do that. Looking into the past, so again, I want to emphasize things we really do know. So looking in the past, there's a graph, and this is 1,000 years from sort of now, going back 1,000 years. This is global temperature, and what has really caught people's attention is the fact that it shoots up in the last 100 years, which is earlier data I showed you. This is the so-called hockey stick graph because it bends like the blade of a hockey stick, kind of what these guys carry around on ice arenas. The global sea level record is possibly not as long, but yet still very good. If you go to New York City, you can go to Battery Park, and you'll see on the waterfront there a little white hut. And sitting there for 100 years, or close to that place, before it was filled, has been a tide gauge, something that measures the height of the ocean in New York and makes corrections for the fact that the land mass is changing height, etc. And the story that emerges is that the global sea level has been rising. It looks like about 20 centimeters over the last century. And in the last decade, it's speeding up a little bit, and now it's rising 20 centimeters per century, or 2 millimeters per year. The last decade, it's rising by 3 millimeters per year. And noticeably, we can see Greenland putting out more ice into the ocean, possibly totally natural. In the past, you should know that this slope can range from this very modest number to being easily 20 or 25 times or even larger. And during those periods of time, the sea level changes within a century a lot, by a meter or 2 meters or so. And that's the question people are asking now. Is it possible that in the next century, or the one beyond, that we would have a rapid change in sea level? So that's the question. That's what has gotten scientists interested in this problem, to look into the past and see rapid change, and to think into the future what may happen. So to end this little piece, this would be my opinion, that for the past, obviously data, while not perfect, is credible. We know what air temperature has been doing for the last millennia and further. And likewise, for sea level, we know what's been happening. Going forward, making a projection, I would argue that for air temperature for the next century, we have a sense of the different amounts of possible greenhouse gases that could be put into the atmosphere. The computer models have been worked on for 5 decades. They're reasonable, and they can project the air temperature going forward. And it looks like the air will warm a few degrees over this century. But that's where I would draw the line and say that when you speak of a projection of sea level, you have to pause, because the science community has produced numbers. Those numbers are the part about the ocean heating and expanding, so that's one part of the story. But the part about the glaciers suddenly speeding up or not and changing sea level do not involve numbers. They're just an asterisk in the report, and they say, we have not addressed this. And many people reacted to that and said, well, maybe that could be the bigger part, or there may be nothing happens, and the current numbers are good. It's that uncertainty that has made people uncomfortable. So that is the main point of that part. So we're zooming into subtopic of subtopic. Once you've considered that ice sheets may play a big role here, then you need to be more specific. This is an unusual projection, but nonetheless, you can see the Earth here. So you have the 2 ice sheets, Greenland here, Antarctica here, which is about 10 times the size of Greenland. And the one that used to exist over New York City and over Canada, the Laurentide ice sheet, is presently gone. During most of the last 2 million years, that ice sheet has been present. It's not greatly understood why those ice sheets come and go. Obviously, the distance between the Earth and the Sun change periodically, and we can see a correlation with that to the appearance and disappearance of ice sheets. But the more nuances of being able to say why one ice sheet disappears, the Laurentide, but not the other ice sheets, Greenland and Antarctica, is the current state of the science. And in this is called an interglacial, the period we are in now, the present 10,000-year period, where we are in a warm period. Most of the time, on the 100,000-year time scale before that, we are in a glacial period. The previous interglacial, sea level was much higher, and the planet was warmer. Looking at this rather specific map leads you to 2 very specific things to look at. Space agencies fly remote sensing vehicles over the Earth, different types of vehicles that can determine the height of the ice sheets, altimeters, can determine the mass of the ice sheets, gravity satellites, and just simply cameras that can watch motion. And over the last decade, as these satellites have been flying around the Earth and looking, the two places on Earth that you see the major change of water are in the ice sheets. They're changing size. And in two particular locations. Among them, in Greenland, a place called Jacobs Harbor, Jakobshavn, and a place in Antarctica called the Pine Island Glacier. So those are two specific places that we'll visit to really focus on what's happening now. The story is in this picture. So again, this is very detailed, but if you're actually going to get to the point of finally making projections, this is the cartoon that one has to fill in. This is an ice sheet on this side, which grows by snow. Under gravity, it flows towards the ocean, and that's one part. It cracks and calves and makes icebergs. The other part is the ocean flows towards the ice sheet. If it's a cold ocean flowing towards an ice sheet advances. If it's a warm ocean flowing towards the ice sheet retreats. And in that case, global sea level goes up. So the fast change on the sea level, the beach where we go and play, the fast change of that on the planet in terms of increase is whenever warm water, represented very simply by this red arrow. And if there's no warm water, then the ice sheet will likely advance or reach a balance forward. But if you have the appearance of these warm water patches coming towards ice sheets, that's really now getting to the heart of the matter scientifically of why it could be, or how it could be, that sea level would change. It's that. The problem with this red arrow occurring near the ice sheets is that you cannot see it by remote sensing. It turns out, so these red waters here are waters that come from the outside the polar regions, ultimately the tropical regions. And the waters are warm and they're salty. So if you go out into the lagoon here, the water is warm and it's salty. Think of the large planet scale of that water heading toward the polar regions, which it does, ultimately. It's not obvious. It's warm water, but because it has so much salt, when it gets near the ice sheets, it sinks below. So it's warm and it's hot. You would think it's light, but it's actually filled with salt, containing a lot of salt, and it sinks. So it travels in underneath, and you cannot see it by remote sensing. You actually have to observe this red water by putting instrumentation into the water. And if somebody has an alternative idea how to do that, how to monitor the ice sheets, that would be great. We would have a way to do it. Right now, there's no other way than actually getting to these places. And the difficulty getting to these places is, as you saw in the video, the icebergs crack off. You cannot get ships into these places. So we have to think about technologies and ways to observe this process. So if you're going to do that, then, if you're really going to ask the question about rapid change in sea level, rapid meaning on the scale of a century, then you want to check and see if those red arrows exist or not around the ice sheets. So this may all seem very specific to you, but I want to emphasize what physically we would need to understand to move this science forward. And the next two little parts are things that I've been doing at NYU with colleagues from other places in trying to make measurements of that red arrow in Greenland and elsewhere. So, starting off from where we are tonight, if you zoom out to the planet, you can see Greenland is that patch sitting up there. And that's the object that we're about to study. This is a NASA animation. And as you zoom in on Greenland, this is sea ice. This is 1 meter thick. This is land ice. This is 1 kilometer thick. I want to bring out that difference, that we're studying land ice, not sea ice, which is a separate thing. So as I said, under gravity, land ice goes from the land and it falls through the valleys into the ocean. And it reaches a place. The coastline is nothing but an ice wall 1 kilometer high. And that coastline here suddenly began to retreat in the case of Greenland, in the case of this fjord in 1997. And people were asking, why would it be that this ice front would start to retreat suddenly in 1997? And that's what got us at NYU interested in that question of why would a glacier change so quickly? And the answer lies in the planet scale. That is, there's lots of warm water in the ocean, the North Atlantic. There's cold water in the polar regions. And essentially what happened is warm water went from here, a little bit of it. The wind changed first. And if you change the wind, you change the ocean current. And the ocean current crashed into Greenland and melted it. You couldn't see it because it was below the surface. As an aside, there is a lot of people who work on policy issues, obviously relating to sea level, and one always encounters these folks in Greenland and Antarctica, and they're there to get a better understanding of the science, and I always find it quite impressive. These people take the time. This is the US Congress Science and Technology Committee, and it's much easier to explain to these folks when you're standing in front of glaciers and a chance to explain the basic science. And there were other people there last year, also from the Royal Scandinavian family, the 3 Crown Prince and Princess came, and we had a week to discuss the science and some of the policy implications. So back to the specific, given this fjord, how is it you're going to get the temperature in this fjord? And I take a box here, and what we've been doing with our graduate students is we've borrowed some technology from the Navy, who use a certain technology to track submarines, and we've tried that out in a helicopter, and it works quite well. So basically, from a helicopter, in this fjord, you cannot take a boat into these places, but you can take these probes, which can be dropped from an airplane or a helicopter, in this case here. And so it's nothing other than a temperature and salinity measuring device. It hits the ocean, and then it falls down for the next 10 minutes through the ocean, and it sends back a report on the temperature. So you have to kind of hover there for 10 minutes, and then you repeat this 10 or 100 times, depending on how many profiles you want to get. And in these places, in these ice-covered regions, this is a Greenland picture where it's mostly icebergs. The surface waters are all cold, and after you go down a certain depth, you get to these other waters, and that's the red arrow I was pointing to earlier. And so the deeper waters are all warm. So from this point of the story, the observation that people were excited about was that in 1997, this fjord and glaciers started to go twice as fast into the ocean, and it seemed quite alarming. Nobody had made any observation to that point. So in 2007 and 2009, we made this observation, and it said, look, in the deep, it's all warm water. That ultimately, parts of the Gulf Stream had found its way into this fjord. And the question is, was the water in that fjord always warm? And there was no historical record, but with some luck, we ran across some data from the Greenland fisheries people. It turns out that people who fish in Greenland, they always put little temperature sensors, not much bigger than this device, on their nets. And so as they trawl over the seafloor to collect shrimp and whatnot, they also measure the temperatures. And they did this for decades. And we were lucky enough to get access to that data. And it was quite remarkable that it showed that the coast of Greenland was cold until 1997. And from 1997 on the west coast until now, it's all been warm. So there was an abrupt change within a year on the coast of Greenland. And we dug a little deeper, and what we found is that the wind blowing from the United States or North America to Europe changed suddenly the year before. So it's a story of rapid change, and one that I guess we kind of guessed might be possible, but to actually see this play out in nature was quite interesting. For the North Atlantic, this may look like a busy diagram, but it's worth looking at for a minute. The basic mechanics of the ocean on the planet, at least for the North Atlantic, is this red gyre. It's warm, salty water coming up along here, the Gulf Stream. Part of it goes to the Arctic. The other part of relevance is this arrow here, and it turns around and it goes into the Labrador Sea. That's the basic transport of warm, salty water. From the Arctic comes blue, cold, and fresh water. It comes along Greenland and comes out and goes underneath. That's the basic physics of the circulation of the ocean. But that diagram is, well, it's nothing more than a cartoon. But what we can see in computer models is that this red arrow shifts from time to time. And in 1997, that arrow went and crashed into Greenland. And that was the story. And this circulation of the ocean exists because of what the atmosphere is doing. The atmosphere has a circulation, and the ocean integrates it or listens to it. And after a while, the ocean begins to behave and do what the atmosphere tells it to do. So the winds changed, and then the Gulf Stream waters crashed over to Greenland. So that's a rather long story, but it's an important story because it's actually what happened. And I would argue you cannot use your mind to figure this out. You can learn it and memorize it. But basically, this is physics, and you can simulate this on a computer, provided you have enough observations. Computer models are good, but they're not yet good enough to capture these kind of nuances of change. We can simulate basic features, but really getting the projections, the timing of change, is a challenge that we have not yet reached. So what I want to leave you on for Greenland is not the idea that you have to warm the ocean in order to change sea level. It's actually a slightly different story. In order to change sea level quickly, all you have to do is change the wind pattern, because the ocean has lots of heat in it. And if you change the wind, it is possible that the warm waters run into ice sheets, and then that is how you get a rapid melting. So a change in the wind changes the ocean, changes the ice sheet, changes sea level. If there is to be a large change in sea level in this century or the next, I find it hard to imagine it would be anything other than that sequence. The wind would change, ocean currents change, ice sheet melts, sea level goes up. On a much longer time scale, a separate story is, forget that, just warm the atmosphere and directly with the atmosphere just melt the ice sheets. And that certainly happens too. Our work was written up 2 years ago in that, and it was reported also in NYU. And it was also caught in an editorial in Science magazine because we had done 2 studies that year. One is the study I just showed you, which is about data. It's what happened in Greenland. In Antarctica, you might guess, or I'll tell you, there is no data because there's nobody there, essentially. So we don't have a data story of what happened. We have a computer modeling story. And again, in that story, we find the same things. For the Antarctic ice sheet, if you change the wind pattern around the Southern Ocean a little bit in a certain way, then the ice sheet responds and melts. The exact same analogy. So it's really this change in winds that I'm focusing on here. And then the question is, why did the winds change? Well, again, we run into our present limitations. We do not have a deep enough understanding of the atmosphere to yet be able to project forward or even backwards these subtle things which are called oscillations. And for those of you more technically inclined, these are called the North Atlantic Oscillation, or the Pacific Decadal Oscillation. There's lots of names for these, but the atmosphere gets into a mood for a decade and does one thing, and then it changes later and does something else. Antarctica, the Pine Island Glacier. While Greenland is an interesting place, in terms of potential large change, it's Antarctica that one really needs to pay attention to. And the reason for that is caught up here. Greenland is largely a piece of ice sitting on land, and the ocean can attack in some places. Antarctica is far more interesting. Antarctica, when you remove the ice, the eastern part is high and dry, but the entire western part, it's already in the ocean. So really, when you think of Antarctica, you need to think of a continent with an ice cap on it, but it has become so big over time, it's spilled over into the ocean. And parts of it that are spilling over into the ocean are the size of Greenland itself. So these are called marine ice sheets. They're pieces of an ice sheet that are already in the ocean. So when you stand on a glacier in Antarctica, it's 4 kilometers high, but the top 2 kilometers are above sea level, but the lower 2 kilometers are already in the ocean. And so that's why people have focused on the West Antarctic ice sheet as the key point about climate change sensitivity and sea level. Getting research support for, just so you know, many countries participate in research in Antarctica. In the US, we spend $300 million a year just for setting up essentially hotels and food. So it's expensive to get people there because you have to fly people in, fly fuel in, and then grants on the order of $10 million allow you to do some research, but I would bring out that the idea of tackling Antarctica and arriving at a credible projection of sea level is much further to go than where we presently go with our commitment. And part of that is tied up in the fact that we have different agencies studying this problem of sea level, but we have not yet reached a coordination and an efficiency, certainly within the US, of putting resources to this problem. So here is Antarctica, and this part is Western Antarctica. This little place here is Pine Island Glacier. And why focus on that? Well, 2 reasons. Most of this is already in the ocean. It's marine. And second of all, as we fly very expensive sensors, remote sensing vehicles, over Antarctica, they always point and they say, take a look right here. This is the place that's changing. It's lowering its elevation the most rapidly. So that's interesting. That's a remote sensing point of view. Another non-obvious fact is if you study the ocean circulation, and you think about where would there be this red vector of warm water crashing into Antarctica? Well, it turns out, if you look at today's knowledge of the ocean, the warm water travels around Antarctica in a circle, the Antarctic Circumpolar Current, and the place that it crashes into the continent is right there. So it looks like, again, we can see this correlation of ocean behavior with warm water and ice sheet response. Our science plan started 3 or 4 years ago, and how much we've achieved in that time is modest, would be an exaggeration of accomplishment. And it's because it is mind-bogglingly difficult to get there and to make measurements. And I'll try to bring that out. So Greenland had these icebergs that were cracking off. Antarctica is a different creature. When the ice goes from the land into the ocean, it forms a feature called an ice shelf. So this is a thick piece of ice, about 1 kilometer thick, and it goes from the land of Antarctica into the ocean. And these ice shelves can be big. For example, the size of France. They're large pieces of floating ice. And the ocean goes underneath these features. And the idea is to get into these places and to set up a monitoring system, much like we have for our modern day weather stations. So in theory, quite straightforward. So we want to, here you cannot use a helicopter, you actually have to drill through. So our plan to do this was to start in New Zealand, and the logistical support one can get from the Air Force is quite good. There are large airplanes, C-17s. These Globemaster can bring you and your equipment to Antarctica. So again, I have to be specific because we're trying to solve a specific problem in a specific place in order to address sea level. And this is, as far as I can tell, how you can do it. And if someone has a better idea, then that would be better. But it looks like this is where we're stuck. you can land here in the first place, which is here in McMurdo. There are about 1,000 people there in the summer. And in order to get out further into the ice sheet, you can go anywhere that there is a runway. Turns out that there's a runway in this place where this red arrow ends, and this is called the Bird Field Station, okay? And that's kind of like a hub in an airport sense, and you can get airplanes from the Air Force. These ones are interesting, these Hercules LC-130s. These actually have skis on them, so they can land on wheels or skis. But they have a limit. They will only land wherever there's a runway, and there happens to be one groomed at Bird Station. But finally, the last part of your journey, if you want to get out anywhere else, you need a smaller aircraft, or you don't need it. It's what you're going to get. And it's called a Twin Otter, a remarkable vehicle that can, instead of taking off or landing across along a runway, it can actually do it across a runway. It's a very versatile vehicle. But again, it's getting smaller and smaller. The upshot is we finally made it to this place with our equipment, and we landed once, and the pilot said, "This is far too dangerous. Everybody has to go away. We can't do it." So that was canceled. So that was kind of disappointing. So the next plan is to think about how are you going to do this. And, well, I think if you put helicopters in this area, you might be able to carry equipment around. And just this last January when I went back, my colleagues from New Zealand, I was quite surprised. So this is the Globemaster, and they just had kind of check-in or carry-on, I don't know what you call it, but they just kind of said, okay, we'll just put our helicopter in there. I don't know if they have to weigh it or what. And so you're flying in the back, I don't know if you can see it, that's their helicopter, and they just carry it with them. Very impressive. This is what happened when the pilot said the season is canceled. We had 2 days left, and so what we could do was put in a weather station. This is what happened. Today we're heading off. If you can see, we're leaving the waste galley where we had a very nice breakfast. And so we're heading out to the Pine Island Glacier up here, and we're going to install an automatic weather station. We hope a weather station will be installed in Antarctica. We've been here 3 days now, and everything's been going just great. You can see in the background, we got the weather tower set up, and to the side of that, you can see the solar panels and wind turbine. It's been very almost balmy here the last few days, and we've also attracted some visitors here, some skua, who are very interested in our presence. More what I was contemplating or expecting for Antarctica. A little bit more polar. It's constantly now about 20 to 30 knots, and with the wind chill, it's pretty cool. Probably minus 15, 20. Makes it a little harder to work on this. We're carrying out research in such remote locations, not because they're remote, but because that's where interesting science is happening, and that's where we have to go to. These places are extremely difficult to get to, and at the moment they're even more difficult to get back from. I mention that because when you are in a location in Antarctica, it's interesting. Wherever you are, and wherever the plane coming to get you is, will not come and get you unless there's a third location with good weather. It turns out that happens very infrequently. And so you say, I'm ready to go home now, and they say, okay, and they call you every day, and this goes on for 2 or 3 weeks until finally it's all good and they come and get you. So it's a long process. This past year, we made another attempt to go out. Again, the idea is from the main base to the hub, out to this. And another example of, I wouldn't say frustration, but of the slowness at which this science is evolving is I went for 1 month to do this, and I got out here, and the window of opportunity in 1 month, the amount of research that you land on the ground and do research is 4 hours. And the rest of the time you're waiting and drinking hot chocolate and more hot chocolate, and it goes on and on. So again, the kind of picture I'm drawing is that we think this is important to global sea level, that in here is somewhere between 3 to 5 meters of sea level change, that it's vulnerable, and if you melt this, it will spread around the Earth, and sea level pretty much everywhere will rise by that amount. But we don't know that. That's just a hypothesis. How it will change is if more warm water comes and attacks it. And again, we do not have a computer model of that system. So we cannot make a statement of when and how much. We can just draw people's attention to it and say, that's interesting, that could change. And we can look into our past and see big change. So this past year, I finally did make it to Pine Island Glacier. And here's a little clip after long waiting, actually landing on the ground, where we were able to do some research. It's Thursday, January 28th, and today we finally made it to the Pine Island Glacier, and here we are, standing near the glacier. Looking to the south, the sky is beautiful, and the sun is setting towards the south. And if you follow me around, it's a little noisy
towards the north
for a moment.
You can see the Hudson Mountains maybe behind me. That's where we're headed shortly, and we're going to install a weather station in that very remote, beautiful location. At the moment, we're stopping at our fuel cache. We have 12 barrels of fuel that we're picking up here, so we can fill up our otter and then move onward. All in all, a pretty good day.
So that is the kind of challenge you have to. In order to get somewhere, there has to be fuel sitting there in order that you can get back. So you have to wait for other bigger aircraft to put fuel ahead and cache it. There we had 12 barrels of fuel, and that was put out. Those fuel barrels are very expensive. If you think of the cost of putting each barrel of fuel on that location, each barrel is probably $10,000 a barrel of fuel. And from here, that's where I kind of want to drop that story. With Antarctica, this is what we are doing, our group. We're involved with 5 universities in the United States, our colleagues in Europe, and we're moving forward at a research pace. I don't know if it's an adequate pace from a societal point of view, but that's where the research stands in April 2010. It's what you saw. One of the things we also like to do is outreach and to train future scientists. Outreach is generally in the form of reports. So this is a United States report, and it's looking at our planet in terms of really in the next century or two, what are the possible climate threats? One is sea level, one is the water cycle, another one has to do with methane gas, and another one is the conveyor belt turning off. So these are identified as the main 4 threats. And the idea of these reports is not to confuse a report with advancing science, but it's really coordinating and synthesizing what we know, which is useful. So we wrote a report about sea level, and the report essentially says what I'm saying to you in my remarks here and there. You may also be familiar on the international level with the Intergovernmental Panel on Climate Change, IPCC. This is ultimately the most authoritative body on climate change. I mentioned earlier that the projections on sea level are less than perfect. That's been acknowledged. And going forward, starting in June in Kuala Lumpur, about 100 scientists from around many countries will get together and begin setting up a more coordinated task to address sea level change. I was also interested to learn, I came across a report that was also, that emanates from here, from the Environmental Authority of the UAE, and it addresses 3 issues in climate change, and one of them happens to be sea level. You can see that part here, which is an analysis of sea level rise, and it brings out points that are known about the globe, but also specific points that are relevant to Abu Dhabi and the Emirates itself. Other things we do are museum displays. Every year at the American Museum of Natural History, we set up displays with little submarines and ice shelves, and we have lots of fun with the kids. We try to communicate the essence of the problem that we study. We also have a video here, which this is the extreme of outreach. This is a little bit, I guess it has an opinion in it, I would say, about climate change. which the creator made. But nonetheless, while it has strong opinions, I think to kids, when we go to schools and that, it sends out a message about the polar environments and climate change. I'll play a little bit of that. And I have to add one other word. This was a guy in Brooklyn who we gave a long list of scientific words, and we said, can you make a rap song? And he said, yes. And if you look at it, he rhymed a lot of scientific terms like climate anomalies and fitted in quite well.
About the earth, really talk about survival. We could talk about the poles where the cold is unrivaled. The Arctic top of the world got people and polar bears. Antarctica, crazy penguins chilling down there on miles and miles of ice and glaciers. But something ain't straight with our polar neighbors. It's a change in the climate, a change in the weather. It's heating up now, but it's not for the better. See, the heat comes down from the sun to the earth, but now the heat can't escape, it just can't disperse because of carbon dioxide from power plants and factories, causing trucks so much more than you could find naturally. So the poles get warm and the earth gets hotter. All that necessary ice melts down into water. And the impact, the sad fact is it can only escalate. So for real, we gotta act now before it's too late.
So what's next? Well, I think looking at an NYU point of view, the way I see that we are going to make our contribution along with our colleagues around the world is that in my institute, which is the Courant Institute, takes a very theoretical and mathematical view on the climate system, which is a contribution. We've also teaming up now with folks at NYU Polytech who have a very much engineering capability. And in particular here, I'm thinking of ways in which automated vehicles, et cetera, can be used to instrument the polar oceans. We also work with our partners in the US Department of Energy. And I really emphasize that this is the world's most powerful computer, Jaguar, and that's what they give us to use for our climate science. So we're really not held up so much by computing power as we're held up by observations and good ideas. But it's nice that these resources do exist, and the Department of Energy are excited to apply them to lead to these projections. And for what it's worth, given the knowledge we have now, next year, we will run a simulation of the entire planet, including the ice sheets, with this computer, or one like it, and at least make some projection, although I hesitate to say how credible that will be in this early time. The other thing we need, our partners around the world, are these things, icebreakers. These are ships that can travel through sea ice. They come equipped with helicopters and other things. So it might simplify the logistics a lot if you can just travel around the edge of the ice sheets, put in automated instrumentation, and simply monitor their behavior. And if we can do that for a decade, 2 or 3, I think we can build data sets where you can just look at them and you can begin to understand how the Earth works rather than trying to maybe guess it. So these vessels exist. The problem with these vessels is there are probably only a half dozen of them, and they're difficult to get. But nonetheless, one would think if people really want to solve this problem, they will mobilize resources to do it. And my university also now is starting up a research activity in Abu Dhabi, and it's possible that that interest can also fit in with these other ones. And going forward, taking our time, these are really complex problems, but I think if we really focus and put together strategies, we can make concrete steps forward. In terms of this report, since I'm here, I'll bring out the essence of what this report. It called for an Abu Dhabi Sea Level Center, and I think that's something folks here should do. And I think it could contribute in 2 ways. This report said that there's lots of words here, but in essence, I think what a climate change center here can do is contribute to the global understanding of sea level, and then also the regional, to think about the Gulf and the surrounding ocean. You cannot solve regional sea level change unless you solve the global problem. So you have to do both. And that's that. So for my part, I think that the theory being developed at Courant can advance with the kind of observational structure. So I think just speaking, looking forward, this report called out for a sea level center in Abu Dhabi to focus on that. And I think if it's really going to have a strong impact, I think the way to do it is to think about how we would build instrumentation to observe many places in the world, none the least the polar regions. So it may seem far away and removed, but if you want to answer the question, then in my view, that's how you need to do it. So in summary, when and how much sea level will change, there is flat out no credible projection. And that's not necessarily a devastatingly bad thing, it's just where we are. I think the international community can solve this problem, but the problem we have here is not so much this word, but it's this word. You have to study the problem for a sustained period, not just a few years. You have to stick with it for like a decade to really begin to make progress. And that's what we're trying to do, is simply that at NYU. We want to contribute that, to give an understanding, and I don't want to, I'll give an opinion. I think it's going to take a long time to do this. But if we don't start, we won't get there. And that's it.
My name is John Roth. I am speaking as the chairman designate of a new foundation which is going to be primarily interested in helping humanity. What is extremely interesting in having listened to you is that we intend to be present in a few geographical areas, all of which you have mentioned as being likely to be subject to the kind of changes that you've been so fascinatingly describing. And I mention in particular, for example, Haiti, New Orleans, Calcutta, areas where obviously for reasons of poverty, an organization that isn't particularly interested in the climate necessarily would have to pay great attention to. So my question to you, what alarms me a little bit, and it's perfectly understandable, it is obviously going to take you and your dear colleagues a long time before you can arrive at any conclusions that might guide us. And there we have problems facing us which are primarily motivated by poverty. And the problem that I see that we're going to have to face is simply this. You are not going to be terribly intelligent if you're going to be spending a great deal of money to try and provide a long-term solution to a problem if you are most likely to run into, excuse me, I'm losing my voice, if you're likely to run into situations where because of climate changes, everything will change. What is your advice? What do we do? Do we simply ignore those areas and say it's too early to work there? Let's go and address problems of poverty where the climatical changes will not have that effect, or what would you suggest? Thank you. Sorry to be long-winded, but it's a complicated question.
It is, and it's one I take to heart. I feel that two things. One is a positive thing and one is a cautionary thing. As a scientist, I think people look to us to have leadership in this area. I'm not sure we have been trained or, to be quite frank, are up to that yet. So you might want to hear some other answer, but I'll give you that one for the moment. Moving to the brighter part of what I think, and I get worried, I have to really say, whenever science and policy begin to mix, because then it becomes opinionated. I really wanted to focus on the science, and my impression is that you got that. You got the science point. And now you're moving to the, appropriately, to the policy point. What I can tell you what scientists are doing is to look to a way to change how we do business. And we'll see how successful, but if I can elucidate it, we are driven by curiosity science, and that's what we've been doing for decades. What I'm doing is curiosity-driven science. I'm curious. It's not problem-based science. And we have different, I'll speak to the United States setup. We have different agencies which at the worst of times compete with one another, and at the best of times don't cooperate. And that's just the way we've established things. So speaking of developed countries, I think a positive thing is we can have our agencies focus together, which have enormous capabilities in space, on the ground, computations, theory. The pieces can be put together, but they somehow have to be organized nationally and internationally by countries that have a capability to donate their effort in this way. So I've seen elements where I think there's hope there, and I think it's even within this year that I think people are getting a sense that we need to do that. So again, I stress with you that if we're going to these places that do not have resources to solve this problem themselves in poorer countries, when we solve the problem for ourselves, we're solving it in a sense for everyone. And all I mean by solving is just figuring out whether or not there's a sea level problem or not. And the way to get to that is to coordinate science activities and say, this is about a problem, and what are you going to do about the problem? Which is different than here's some effort, some funds, some resources, and do whatever your peers think is really cool. And I think that's great stuff, and that's what we're doing. But I don't think what we're doing leads quickly to an answer. And so who's responsible for changing the way we do business, not in a dramatic way, in a modest way, just to solve a problem. And it's about having an intention and a focus on a problem, saying, I got it, we're trying to do that, so let's do it. So that's rather long-winded. I think there were bright moments of that and darker moments, but that's what it looks like.
Tamsin Carlisle, I'm with the National newspaper here. The big missing part of the puzzle, what made the winds change? You say the climatologists don't really understand what's going on yet, but do you have any theories? And if so, can they be tested?
Where we've made it presently is just thinking about the atmosphere and the planet. I'll just give you not a thought experiment, but a computational experiment. If you take an atmosphere model of our planet and you fix the status of the ice in the ocean, you just hold it in place and do not let it change, or the land, and you just let the atmosphere run wild for 1,000 years. And then you look back at that model record, you see periods in there when the winds take a certain pattern for a decade, and then for another decade they switch, and then sometimes they flick back and forth. It may not be obvious, but the ocean, if the winds flick around all over the place, the ocean doesn't do anything. But if the atmosphere gets organized and directs in a certain way, the ocean listens and integrates and moves. So getting back to that record, to my understanding, people do not understand why those oscillations occur, and that somebody more expert than me can address that. For sure, I can say the ability to project and say when will those oscillations occur, that capability does not yet exist. And I think that's why we're doing the research. We being, when I go to a meeting, there are 12,000 people there, lots of people. So there are folks working on this, and these are hard problems. Does that help answer? Well, one idea would be, for example, if you look at the Pacific Ocean, back over yonder, the famous oscillation there is called El Nino, and that's pretty well understood, that the atmosphere changes, it oscillates in strength, and that has to do nothing other than the temperature of the ocean below it. So if the temperature of the ocean is hot or cold, it causes wind patterns. But then the wind patterns move the warm water around, and that changes the atmosphere. So it's a loop. That loop for El Nino is pretty clear. it produces an oscillation of 3 to 5 years of El Nino events. The oscillations for these other patterns, ultimately, it seems that in part, they exist in the atmosphere naturally, and maybe that means the atmosphere is just a chaotic system and just wobbles around in different fixed points, or that it's driven by the ocean in a more predictable, projectable way.
Hello. Hi, my name's Brad. I'm just an average person. I'm not with the National or anything. I'm just curious, you know, you're American. The US has a fairly major amount of influence in a variety of different areas, either publicly or privately. What level of enthusiasm does the US government have to support the findings that you're trying desperately to coordinate through sustained resources and all the rest of it? Are they very keen to get to the bottom of this? What's in it for them? And is there obstacles that may or may not be that apparent that you may be coming up against in terms of coordinating the resources required to actually get to the bottom of all of this?
My sense is that, surprisingly, we'll see, but in the last even 6 months, there's kind of a softening and a change of attitude, a willingness to want to solve this problem. And so that's a very positive sign emanating out of these different entities. To be quite frank, if you look at it, entities called agencies, which exist in all countries to support things, have self-interest, and one has to find ways to make these self-interests meet. I'm certainly not going to say to agencies, do this. Instead, what we're doing as a group of scientists is trying to point out the advantage of them collaborating and bringing their own strengths. And it looks like we're making some progress. We'll hold several meetings this year. I mentioned one for IPCC in June in Kuala Lumpur. It will be 100 scientists coming together with agency representation. In July in Washington, D.C., we're having a meeting with nothing else other than what are we doing about sea level? And we're bringing the agencies in and to say, to please listen, and do you want to coordinate? So we're not looking for crazy steps in order to make progress here. It's rather modest steps just to tilt resources towards saying, do this. So in a sentence, I think it looks good, but we'll see.
Christopher Coleman, I'm just an interested individual. I understand the difficulty in obtaining data, but are you able to put upper and lower bounds on what that wanted data might be if it existed, and using those upper and lower bounds to put upper and lower bounds on the amount of sea level rise that we could expect? Okay.
The upper bound that is not helpful, let's just start there. In terms of sea level rise, let's just talk about positive numbers. You could also have sea level decreasing. The upper bound will be the amount of ice in Greenland, which represents 7 meters of global sea level change. West Antarctica represents 5 meters of global sea level change. East Antarctica represents 60 meters, 60. But East Antarctica is largely high and dry, and I think you have to melt it directly, and that will take a long time. So for my first bound, I would put West Antarctica as 5 meters, part of Greenland, a couple of meters. See, this is all very hand-wavy, but just try to answer your question. So in this space of 8 meters of sea level change, when it could happen, well, I would, looking into the past records, you can see periods when sea level went up by several meters per year. So I would think that easily within 200 years or something on that scale, it is plausible, now my arms are waving, they're actually coming out of the socket, that that's the kind of number, and we may see absolutely nothing. We'll just see the 30 centimeters we're seeing now. So you see 30 centimeters a century, and the upper bound is, pick a number, 2 meters or something like that. That would be my hand-wavy argument.
Hi, my name is Luca. I'm an architect working here in Abu Dhabi. Question is, I'm plenty ignorant about the issue about science behind the sea levels, but I would have expected some mentioning about rivers and how rivers are within the pattern and within the frame of the science, because we know that rivers are the amount of water the rivers are putting into the ocean is basically going down because of the anthropic pressure in the developing countries. So is this within the picture? Is this within the picture of the worst case scenario of the +7 meters?
My impression, so when people, I've presented you an extremely narrow view under the hypothesis that the dominant signal are these ice sheets. There are also little things called ice caps, like on the Himalaya and Alaska. There are other features. You're talking about groundwater, which is essentially rainwater on the surface making rivers, or water penetrating the land and coming into the ocean, groundwater. I'm not an expert in that. The people who study that do not put big numbers on that. I think it's meaningful, but it's not, I don't think it's the hammer of change.
Hi, my name is Khizer. I'm from the National Bonds. My question is, if we talking about the natural cycle, like melting, and due to the heat, the melting, then it's clouds, evaporation, clouds and rain. So this evaporation is not equalate, like there's no any equilibrium about this. There's like because if the heat is increased, the evaporation will be increased. So these are not balancing to each other.
My interpretation of your question is, would you expect the planet itself to have an equilibrium? That is, for everything just to kind of stay fixed and in balance. And I think the answer is no. I think naturally the planet will oscillate and do things as an internal system. The main forcer we can see in a historical context is the distance from the Earth to the Sun is very easy to predict. It changes on 20,000-year cycles. And as the Sun gets further, big ice sheets grow over New York. The Sun gets closer, they go away. So there's that forced variability. The system has natural variability. I told you about Greenland. It changed in 1997. It suddenly went faster. It also happened in 1929. So twice in the last century, a similar event happened. Is that natural, or is that forced by our behavior in the atmosphere? To be determined. But natural change occurs all the time. And it's hard to believe this system, for reasons I don't want to expound, it's hard to believe when you move heat around naturally in the ocean and the atmosphere is doing things, complex processes with clouds and that, it's hard to believe this system really gets into a steady state and locks and doesn't just change naturally and make corrections. But maybe I'm not answering your question. Right, so right now, for Greenland, Greenland grows because the ocean evaporates and puts snow on Greenland. So Greenland gets bigger, but the ice at the edge breaks off and calves. Right now, the break-off is bigger than the accumulation. So right now, Greenland is getting smaller by 400 cubic kilometers per year. And that's why it's, at the present moment, it's getting smaller. Okay.
Amin Hashmi, geography student at Paris Sorbonne University. You talked about what they write in the magazines about the predictions of sea levels, and you said, did you say that is actually all wrong because you don't have any real predictions?
No.
And secondly, you talked a lot about funding, and how big a restraint is that on your research?
Right. So what the public media do is quite natural. They catch this sense that there's an environmental problem, if you want to call it that, and then they talk about it, and I think that's natural. It raises public awareness. But I'm not always clear that they bring out the state of the science, which is what I'm attempting to do here, and I suppose that's my job to do that. So I do not say they're wrong. I think they're ahead of me in their own media sense. In terms of funding, adequate funding, I think the nations of the world need to figure out the impacts, the costs of this potential problem, I think, are a big number, and the resources that need to go to it would have to be some small fraction of a big number, and that's not where we are now. But I again stress, I think buried in our system somewhere is this capability already.
Good evening. My name is Emma Chalkoch. I'm with the United Nations Environmental Program. So far, you have been talking about the research of showing how the sea level is rising and what's affecting the sea level to rise. Have you thought about any action plan in terms of how to prevent it from continuing or kind of to try to stop it from happening and from ice sheets melting on?
So that's not my area of expertise, but I can tell you what people talk about, and you may know more about it than me. In terms of looking forward in the next century or two, obviously you either dig in and put a wall around your city, or you kind of get up and move. Those are the two options, I think, on the table. That I haven't really pushed into that area. The only thing I could suggest that I think on the science side that we can contribute is that if we can build credible computer models of that feature there, the Earth system, then I think you can play experiments and you can look at the role of carbon dioxide, you can look at the role of natural variability on the planet and run simulations, and you can get a sense of, on a time scale that means something to people, 50 years, even 100 years, what is the envelope of change, and then you can just pass off that information. I think that's the best that science can deliver on that, are these quantifications, these estimates, under different experiments.
David Woodward, I work for Mubadala in this office. You said that the temperature changes over the next 100 years can be forecast reasonably reliably. My understanding is that the range is something like 2 to 6 degrees Celsius. But there still seems to be a lot of uncertainty and debate about how much is natural, how much is man-made, etc. As I understand it, you're not denying the uncertainties there. You're just saying that those are relatively well defined in comparison with the predictions of sea level rise that will result from global climate change. Is that correct?
That's exactly right.
Thank you.
Okay.
Hi, my name is Ekaterina Tanakova. I'm actually here just as an individual, but I'm a teacher by training, and I have some kind of practical question, and maybe I just got it wrong, but I believe you mentioned that you are planning to have some observation group here in Abu Dhabi that will be taking some measurements of sea level or something. I just wonder what is the base of this group, who will be doing this research and how will it be taken care of? Because I'm also a parent of American community school student, and I know that they have a green team there, and I know that they do a lot of community projects, so I just wonder if it's anything that we could be connected to.
Okay. So that was just a kind of a sketching in my mind that I see two activities. I see that my university is starting an academic and a research enterprise here, and people will have problems to address. So I suggest a problem to address would be the question of global sea level change. I also noticed that the Environmental Agency created a report in January in which they identified, well, at least they put it as problem number 1, sea level and coastal change. And the report said, practical thing is to set up a sea level center here in which it would address these problems so that regional projections can be created here and people can use it for city planning, etc. So my interpolation of those two pieces is that the powerful way to make a contribution is first you have to go global. You have to understand how the planet changes. That's the only way you can deliver information back to the Gulf, and thereby you contribute to the whole planet. The most powerful way to do that, I believe, is through setting up strong observational networks. And it's not infinite. It's simply, this is a vast unknown. There are not many observations here. So to put in, we have observation networks about. We have floats running through the ocean. So it's just moving a step forward in observational environments, albeit, I hope I brought out, challenging is the word. The seasons are very short. And a place like Abu Dhabi, if it really wants to make a concrete contribution that really matters to people, it's to take forward the observational network of, for example, this problem. And what it would look like is to be defined. But it's certainly what's needed is this ability to observe, and you'd have data records that begin to span a decade or 2 decades. And I think that would change the science game. So it doesn't exist, but I hope people think about it.
Hi, my name is Laverne Hagem. I just have 2 questions, and one more serious and one a little bit more lighthearted, I hope. But I would really wonder whether you can challenge, through your institute, the media to represent this science more accurately, as you have tonight. It's very frustrating for engineers, for the public, to really get a grasp on this. Is there any way your institute can influence the media to portray this problem and the acquisition of the data for this problem in a more realistic and logical manner instead of through hype? Yeah. So that's the first question. The second question is, where are we in this sine wave, in this 20,000-year cycle of proximity?
Right. For the sine wave, I think we're coming towards the end of it. But I think, so the last 1 million years, or last 2 million years, have seen 8 major ice ages. Most of the time the planet's in an ice age. It has these little brief periods like now, 10 or 20,000 years of not. My impression, I have to check, is that we're coming out of the warm period. The thinking is that we are putting greenhouse gases into the atmosphere and that we may stay in a warm period. So the thinking is we might override the power of the Sun-Earth distance, which is possible. As for influencing the media, first the funny part, maybe funny. Most of the time I sit down with the media, I think we're having a conversation, and then I read the next day and I'm like, I wonder who they talk to. So, and I guess it sounds like making fun of the media, but there's something broken there, and I don't know that I can solve it, but I experience it. So it's not that we're not trying.
I guess my question goes to, you speak about resources, and you're borrowing the resources of New York University. Obviously, there's a lot of resources available in Abu Dhabi and other people that are committed to environmental concerns. Can you use the power of those resources to be more, to force the media to be more logical and more accurate?
I'm totally with you, because I think there's a breakdown between us creating information when we do it, and you receiving it. It's going through this other process. Yeah, so, right. So I think what we could do, since we have capability, we have time on our hands to do stuff, I think I take that point, and we can work at that, and we can actually set aside resources for communication. And so, yeah, so I take that to heart, that there's big value in that.
Can I just have back at that one? First of all, please note, I'm in the media. I'm here, sitting and listening to your lecture. Now, whether I do a good job of reporting that or not, you'll have to be the judge. But I am here, listening to you. That's number one. Second point is, I think one thing that needs to be done is basically the media have to have enough money somehow, and God knows they're not getting it now, to pay specialist reporters who have the capacity to understand what's being told them in specialist field. Some poor hack who has to cover, 6 different things on 6 different days is not going to make a good job of it.
Excellent point. So there's an example of... That's really good. So we have to face realities, and there are different ones like that. So yes, both your points are good. This reminds me of my last job interview.
Mohammed Hadiri with ADCO. A quick question. The ice sheets are only over Greenland and Antarctica? There's nothing over the Arctic or?
Yeah, so over the Arctic Ocean, it's called sea ice. It's 1 meter thick. So the Arctic Ocean, well, it's an ocean, and the ice can only get roughly 1 meter thick. And the fascinating story of the Arctic sea ice is that in the last 5 decades, half of it has disappeared in essence. So I haven't spoken about that, but that's an amazing story of climate change, natural or forced, it doesn't matter. Huge change in Arctic sea ice. I'm only talking about ice on land called ice sheets, which are very thick, several kilometers.